Everything you have ever touched felt completely, reliably there. The floor under your feet, the chair beneath you, your own hands solid, definite, present whether or not anyone was looking. For 200 years, physics agreed. Then, a little over a century ago, the most careful scientists who ever lived were forced to give that feeling up. They found that at the smallest scale, the particles you are made of have no definite position and no definite motion until the instant something measures them, not because our instruments are too crude, but because there is no settled answer there to find. The most precisely tested theory in the history of science says that reality, underneath, is not a set of facts. It is a haze of possibilities that turns solid only when it is forced to. So here is the question we will sit with tonight. If the world holds no settled state until it is measured, what is it doing when no one is looking? Get comfortable and settle in. Hit subscribe if you're new here, because by the end of this, the solid world you have trusted your whole life is going to look like something the universe quietly assembles on demand. Now, let's slowly ease into this. Part 1. The world that felt solid. The world feels solid. Reach out and rest your hand on the nearest surface, a table, a wall, the arm of whatever you are sitting in, and the message that comes back is immediate and absolute. Something is there. It has edges, it has a place, and it would go on being there whether or not you decided to touch it. It was there a moment ago when you were not thinking about it at all, and it will be there after you stop. This is the most basic report your senses ever hand you, and for almost the whole of human history, physics agreed with that report completely. The task of science, on this older and very comfortable view, was simply to measure a world that was already, definitely, reliably there. For roughly 2 centuries, that assumption held without a single crack running through it. The physics of Isaac Newton described a universe of solid objects following exact paths, like clockwork built out of matter. A planet had a position and a speed at every instant, whether or not any astronomer happened to be watching it. A cannonball traced a curve that existed in full, even in total darkness. If you knew where everything was and how fast it was moving, you could, in principle, calculate the entire future and reconstruct the entire past. The world was a machine of definite parts, and those parts kept their properties to themselves, privately, at all times. Nothing in the universe needed to be observed in order to be exactly what it was. This vision had a name and a mascot, conjured by the French mathematician Pierre-Simon Laplace at the start of the 1800s. Imagine, Laplace said, a mind that knew the exact position and motion of every particle in the universe at a single instant, and that had the power to calculate without limit. For such a mind, nothing would be uncertain. The entire future, down to the last detail of every life that would ever be lived, would lie open before it, like a page already written, and the entire past could be read backward with the same perfect clarity. Nothing would be left to chance, because in this universe, there was no such thing as chance-only causes we happened not to have traced yet. Randomness, on this view, was never a feature of the world. It was only the name we gave to our own ignorance. When a coin landed heads, it was not because the outcome was undecided. It was because we lacked the patience to track every push of air and twitch of the thumb that had fixed the result from the start. The dice of the world were always loaded, always determined, and the only thing ever missing was information. For 100 years, this was not merely one idea among many. It was what it meant to do physics at all, and it worked so well that the universe seemed all but solved, with only a few small details left to tidy up. That picture is the one almost everyone still carries quietly in their head. It is the picture your daily life depends on, and it works so well that questioning it sounds almost foolish. And yet, beginning a little over a century ago, A small group of physicists were slowly forced to give it up, not because they wanted to, but because the universe kept handing them results that the comfortable picture simply could not hold. What they found, piece by reluctant piece, was that underneath the solid world there is something that does not behave like a thing at all. At the smallest scale, the scale of the particles that make up that table and that wall and your own hand, nothing seems to have a single, settled state just sitting there, waiting to be read off. The properties we treat as obvious where something is, how fast it is going, do not appear to exist in a fixed form until the instant the world is forced to commit to an answer. Here is one way to hold that idea before we have actually earned it. Imagine that reality, far down at its base, is not sharp but blurry. Not blurry because our eyes are weak or our instruments are crude, but blurry in itself, genuinely undecided, a smear of possibilities rather than a single fact. And imagine that the act of measuring one piece of the world, bumping into another, and registering a result is what pulls that blur into focus, selecting a single outcome from many and leaving you with the crisp, definite world you believe you live in. That blur, and the strange way it sharpens only when something looks, is the thread we are going to follow tonight. Keep the image somewhere close. We will return to it more than once, and by the end, it will mean something very different than it does right now. The word people reach for, when they first feel the full weight of this, is often a frightened one. But the fear is not the kind that comes from danger, and nothing here can hurt you. It is the quieter vertigo of having the flaw of your certainty gently removed, of realizing that the most obvious fact you know, that things simply are what they are, may be the one thing the universe never actually promised. That feeling has a strange way of turning, if you sit with it long enough, into something closer to wonder. The people in this story felt the fear first. The wonder, for most of them, came later, if it came at all. If any of this sounds unsettling, you are in excellent company, because it unsettled the people who discovered it far more than it is likely to unsettle you. The story we are going to walk through, slowly and in order, is not really the story of a single experiment or a single genius having a single good idea. It is the story of how an entire generation of the most careful thinkers who ever lived stumbled into a truth that frightened them, argued about it for decades, and tried more than once to make it go away. It begins with a quiet, conservative German physicist who broke the smoothness of the world almost by accident and spent years wishing he could take it back. It runs through Albert Einstein, who helped build the new physics and then refused, to the end of his life, to accept where it led. It passes through a young man alone on a barren island in the North Sea, a cat that is somehow both alive and dead, and a long, patient argument between two friends who never stopped disagreeing. And it ends, in our own time, with an experiment that finally settled the question and returned an answer that almost nobody found comforting. Tonight, there is nowhere you need to be and nothing you need to solve. You can let these ideas arrive at their own pace, in the same order the physicists themselves received them, one reluctant step at a time. There will be no math you need to follow and no test at the end. There is only a slow walk through the strangest thing human beings have ever discovered about the world they are made of. So settle in, get comfortable, and let your attention go soft. We are going to start at the beginning, in the last days of the 19th century, with a problem that looked small and tedious and turned out to be the loose thread that unravelled everything. It had to do, of all things, with the colour of light coming off something hot. And the man who finally solved it did not realise, at first, that he had just ended one age of physics and quietly begun another. Part 2. An Act of Desperation. The revolution that dissolved the solid world began with a problem about the colour of heat. In the closing years of the 1800s, this was thought to be one of the dull, nearly finished corners of physics. Everyone already knew the basic fact from ordinary life. Heat a piece of metal and it begins to glow. Warm it gently and it gives off a dull red. Push it hotter and the red brightens into orange, then yellow, and if you could heat it far enough without it melting, the glow would climb toward a brilliant blue-white. The color of a hot object tells you its temperature, which is why a blacksmith can read the heat of iron by eye, and why the surface of a cooler star burns red while a hotter one burns white. The link between heat and color was old, familiar, and seemingly harmless. The question physicists wanted to close out was simply this. For an object at a given temperature, exactly how much light comes off at each color, each wavelength, across the whole spectrum? They wanted a single clean formula that would draw the curve a little energy at the long red wavelengths, rising to a peak, then falling off toward the short blue ones. It seemed like the kind of tidy problem that the powerful physics of the age ought to finish off in an afternoon. Instead, when they fed the situation through the trusted laws of the time, the laws produced a catastrophe. The accepted physics predicted that a hot object should pour out more and more energy at shorter and shorter wavelengths, without limit. As you look toward the blue end of the spectrum and beyond it, into the ultraviolet, the predicted energy did not peak and fall the way real objects do. It climbed toward infinity. Taken at face value, the theory said that every warm object, a kettle, a coal, your own body should be blasting out an infinite amount of energy at the short wavelength end, mostly as ultraviolet light. This was so obviously, almost comically wrong, that it earned a name that captured the embarrassment, the ultraviolet catastrophe. Reality did not do this. The glow of a hot object rises to a peak and then falls away, calm and finite, exactly as your eyes report. The best physics in the world predicted an explosion of energy that simply was not there. Into this gap stepped a man almost perfectly designed to resist a revolution. Max Planck was a German theoretical physicist in his early 40s, profoundly conservative by temperament, devoted to the classical tradition he had inherited. He was not a wild thinker hunting for a new world. He was a careful one, trying to repair an embarrassing hole in the old one. For months he worked on the problem of the glowing object, and at last, in the year 1900, he found a formula that fit the real curve perfectly, across every wavelength and every temperature that had been measured. But the formula came with a price he never wanted to pay. To make the mathematics produce the right answer, Planck had to assume something that violated everything classical physics believed about energy. He had to assume that the hot object could not give off energy in any smooth, continuous amount. Instead, energy could only be emitted or absorbed in discrete, separate packets, little indivisible lumps. The size of each packet was not arbitrary. It was set by the frequency of the light, multiplied by a new constant of nature. The energy of a single packet equals that constant times the frequency. The higher the frequency, the bigger each individual lump of energy has to be. That new constant, we now call it Planck's constant, turned out to be one of the smallest numbers that appears anywhere in science. It is a decimal point followed by more than 30 zeros before the first meaningful digit arrives. Its very smallness is the reason nobody had ever noticed the lumpiness of energy before. The packets are so absurdly tiny that in ordinary life, energy looks perfectly smooth, the way a beach looks like a continuous surface until you kneel down and find it is made of separate grains of sand. Planck had just discovered that the universe, at its base, is grainy rather than smooth, that energy comes in indivisible pieces, and there is a smallest possible step. Now picture the moment it came together. It is late in the year 1900 in Berlin. Max Planck sits at his desk in the lamplight with the finished formula in front of him. On paper, it is a triumph. It matches every measurement. It closes the embarrassing hole. It does exactly what he set out to do. And he cannot bring himself to be happy about it. He keeps turning the assumption over in his mind, the strange, necessary lie at its center, that energy comes in lumps. He does not believe it describes anything real. He tells himself it must be a mathematical trick, a bookkeeping device, a temporary scaffolding he will quietly remove once he understands the problem better. He is a careful man who has just been forced to write down something reckless, and he knows it. The numbers are correct. The meaning is unbearable. He sets down his pen, having ended an age of physics, and he goes to bed convinced he has merely patched one. Planck himself later gave the clearest possible description of what he had done. He called it an act of desperation. He explained that he had been willing to sacrifice any of his previous convictions about physics because a theoretical interpretation simply had to be found, at any cost, no matter how high. Those are not the words of a man announcing a discovery. They are the words of a man confessing to one. And he spent the next decade and more trying to undo it, searching for a way to derive the same correct formula without the lumps, to fold the quantum back into the smooth classical world he loved. He never managed it. The packets were real, and they would not go away. There is something quietly tragic in this, and it is worth holding on to, because it is the first appearance of a pattern that runs through the whole story. The man who opened the door to the strangest physics ever discovered was a man who desperately did not want the door to open. He was not rewarded with delight. He was handed a result he found almost intolerable, and a lifelong, losing argument with his own mathematics. The person who cracks the world open is not always the one who wanted to, and sometimes spends the rest of his life wishing the crack would close. Planck would live long enough to see his reluctant little constant become the foundation of an entire new physics, and to receive a Nobel Prize for it, and still he would carry the unease. He had been desperate, and the universe had taken him at his word. It is worth pausing on just how strange Planck's position was, because it is unlike almost any other discovery in science. Usually a scientist fights to convince a doubting world of a new idea. Planck fought to convince himself that his own idea was not true, and he lost that fight. For years he treated the quantum as a provisional assumption to be justified later by ordinary physics, and he kept expecting the lumps to dissolve back into a smooth, continuous world once the mathematics was properly understood. They never did. The evidence for them only grew, especially after a young patent clerk took them far more seriously than Planck ever had. By the time the rest of physics was ready to embrace the quantum, its own discoverer was still, quietly, hoping it would go away. There is a particular loneliness in that to have your name fixed forever to a revolution you spent years trying to prevent, and to be handed the world's highest honour for a result you privately wished had turned out to be wrong. For now, hold on to two things, because both will matter more and more as the night goes on. The first is that single tiny constant, the smallest meaningful number in physics, the size of the grain. Almost every strange thing we are going to meet, the uncertainty, the blur, the limit on what can be known, is set by the size of that one number. The second is the feeling in that Berlin study, the feeling of a careful person who has found the right answer and wishes with all his being that it were wrong. We are going to see that feeling again on faces far more famous than Planck's. What Planck would not do, someone else was about to do for him. Within 5 years, a young clerk in a Swiss patent office, almost unknown, would pick up Planck's reluctant little packets, and instead of treating them as a trick, he would take them with complete seriousness. He would say something even Planck found outrageous, that the lumps are not just a quirk of how hot objects emit light, but that light itself, all light, everywhere, is made of them. And with that single step, the strangeness would escape the narrow problem of the glowing object and begin to spread through the whole of physics. Part 3. The lump in the light. Light is the most familiar thing in the world, and in 1905, a young man almost nobody had heard of decided it was made of pieces. His name was Albert Einstein, and at the time he was not a professor or a famous scientist. He was a clerk in the patent office in Bern, Switzerland. evaluating other people's inventions during the day and working through the foundations of physics in his spare hours. That single year would become known as his miracle year, because in it he produced several papers that each, on their own, would have made a career. One explained the jittering dance of tiny particles suspended in water and gave near-final proof that atoms are real. One laid out special relativity and rebuilt our understanding of space and time. One contained the most famous equation ever written, the relationship between energy and mass. But the paper Einstein himself flagged as the truly revolutionary one, the only one he described that way, was about light, and it is the one that matters for our story. The puzzle Einstein took on was a small, stubborn laboratory effect called the photoelectric effect. When you shine light on a piece of metal, the light can knock electrons right out of the surface. That part was known. The strange part was the pattern of when it happened and when it did not. According to the accepted wave picture of light, brightness is energy. A brighter light is a bigger wave carrying more energy. So a bright enough light of any color should eventually shake electrons loose. And the brighter you made it, the faster those electrons should fly out. That is the sensible classical expectation. The experiments flatly refused to cooperate with it. What the experiments showed was this. Below a certain frequency of light, a certain color, no electrons came out at all, no matter how bright the light was. You could shine an intense red light on the metal for as long as you liked, and nothing happened. But once you crossed that threshold frequency, moving toward the blue and ultraviolet end, electrons immediately began to fly out, even if the light was extremely faint. And making the light brighter did not make each electron come out faster or with more energy. It only made more electrons come out. The energy of each ejected electron depended only on the color of the light, its frequency, and not on its brightness at all. The wave picture had no way to explain this. A faint high-frequency light should have been gentle. Instead, it was the only kind that worked. Einstein's answer was to take Planck's reluctant packets and push them much further than Planck ever would. Planck had said that hot objects emit energy in lumps, but he still imagined light traveling through space as a smooth wave. Einstein said no light itself, everywhere and always, is made of discrete packets of energy. Each packet, which he called a light quantum and which we now call a photon, carries an amount of energy set by exactly the rule Planck had found. The energy of one photon equals Planck's constant times the frequency of the light. A high-frequency photon toward the blue is a big individual packet. A low-frequency photon toward the red is a small one. With that one move, the whole strange pattern fell into place. Knocking an electron out of the metal takes a certain minimum amount of energy delivered all at once. Light arrives in single photons, and each electron is freed, if at all, by absorbing a single photon. A red photon is too small a packet to do the job, so no matter how many of them you throw at the metal, no matter how bright the red light, not one of them can free an electron. A blue or ultraviolet photon is a big enough packet to knock an electron loose in a single hit. Making the light brighter just means sending more photons, which frees more electrons, but it does nothing to the energy each one delivers, because that is fixed by the frequency. Every piece of the puzzle that the wave picture could not touch, the particle picture explained at once. This was a genuinely radical claim, far more radical than Planck's. For most of the 19th century, physicists had worked hard to prove that light is a wave, and the evidence for that was overwhelming and correct. Light bends around corners, spreads out, and forms interference patterns, all things waves do and particles do not. Now Einstein was saying that light is also, somehow, a stream of particles. Not that physicists had been wrong about the waves, but that light is both at once, and that its particle nature shows up plainly the moment it hands its energy over to matter. Almost no one believed him at first. It took more than a decade and a long campaign of careful experiments before the physics community accepted that he was right. The resistance was so strong that even the experiment which finally settled the matter was carried out by a man trying to prove Einstein wrong. The American physicist Robert Millikan spent years, through the 1910s, performing painstaking measurements of the photoelectric effect, convinced that Einstein's light quantum idea was reckless and that his own careful work would expose its flaws. Instead, measurement after measurement confirmed Einstein's equation exactly. Millikan had, despite himself, produced the most precise proof yet that light delivers its energy in discrete packets, and he reported the result while still grumbling that the underlying idea seemed untenable. This is a pattern that should be starting to feel familiar. Again and again in this story, careful people set out to defend the comfortable, continuous, definite world. And again, their own honesty forces them to hand over fresh evidence against it. The universe kept winning these arguments, not by persuasion, but by the stubborn refusal of the data to come out any other way. Einstein's light quanta were real, whether anyone liked them or not, and the people who liked them least often proved them best. When the acceptance finally came, it came at the highest level. The Nobel Prize in Physics that Einstein was eventually awarded for the year 1921 was not given for relativity, the work he is most famous for today. It was given, in the committee's careful words, especially for his discovery of the law of the photoelectric effect for the light quanta. The most celebrated physicist of the 20th century received his Nobel Prize for proving that light comes in lumps. And here is where the long irony of this story begins to take shape. Einstein, more than anyone, made the quantum physical. Planck had treated the packets as a mathematical trick and tried to explain them away. Einstein insisted they were real features of the world, and he was right, and the whole edifice of quantum physics rose on the foundation he helped lay. Yet within 20 years, this same man would become the most powerful and persistent critic the new physics ever faced. He would spend the second half of his life arguing that quantum mechanics, the theory he helped invent, could not possibly be the final truth about reality. The man who let the quantum loose would spend decades trying to put a leash on it. We will come back to that argument, because it becomes the center of everything, but not yet. For now, notice what has happened to the solid, classical world in just 5 years. Planck has made energy grainy. Einstein has made light into particles that are also waves. The smooth, continuous universe is developing more cracks, and the cracks are spreading from the glow of hot objects into the nature of light itself. The next crack would open inside the atom, inside the very building block of matter, and it would be the strangest one yet. Because to explain why atoms are stable, why the stuff of the world does not instantly collapse, a young Danish physicist was about to propose that electrons can move from one place to another without ever passing through the space in between. Part 4. The atom that made no sense. By the early 1900s, physicists had finally looked inside the atom, and what they found should not have been able to exist. The picture came from Ernest Rutherford, who in 1911 fired tiny particles at a thin sheet of gold foil and watched how they bounced. Most passed straight through, but a few ricocheted back as if they had struck something tiny and impossibly hard. From this, Rutherford worked out the structure of the atom. Almost all of its mass sits in a minuscule, dense, positively charged core, the nucleus, while the much lighter, negatively charged electrons occupy the enormous empty space around it. The atom is mostly nothing. If you scaled the nucleus up to the size of a marble, the nearest electron would be hundreds of meters away, with empty space in between. The solid matter you lean on is, almost entirely, vacancy. That image is the one most of us still picture, a little solar system with electrons circling the nucleus, like planets around the sun. It is a beautiful picture, and, according to the physics of the time, it was fatal. The trouble is that an electron moving in a circle is constantly changing direction, which means it is accelerating, and the well-established laws of electricity and magnetism say that any accelerating electric charge must continuously radiate away energy as light. An orbiting electron should therefore be pouring out energy every instant, losing speed as it does, and spiraling inward toward the nucleus. The calculation is not subtle. An atom built this way should collapse, with the electron crashing into the core in about 100 millionth of a second. Every atom in your body, every atom in the universe, should have imploded in a brief flash of light long before anything could be built from them. Matter, according to the best physics of the age, simply could not be stable, and yet there it sat, all around, stubbornly existing. The man who broke this deadlock was a young Danish physicist named Niels Bohr, who would become one of the towering figures of the century and the patient centre of nearly every argument still ahead of us. In 1913, Bohr made a set of proposals so bold they amounted to changing the rules by decree. He declared that electrons cannot occupy just any orbit around the nucleus. They are allowed only certain specific orbits, at certain specific energies, like steps on a staircase with nothing permitted in between. And while an electron sits in one of these allowed orbits, Bohr said, it simply does not radiate. It does not lose energy. It does not spiral in. It just stays there, stable, in defiance of the classical law that said it should glow itself to death. He offered no reason why. He simply said, the atom behaves this way because that is what it would take for atoms to exist. Then came the part that still stops people cold. An electron can move from one allowed orbit to another, but only by jumping between them. When it drops from a higher energy orbit to a lower one, it gives off the lost energy as a single photon, with a frequency set by exactly how much energy it shed. When it absorbs a photon of just the right energy, it leaps up to a higher orbit. These are the famous quantum jumps. And a quantum jump is not a journey. The electron does not travel from the higher orbit to the lower one, sliding through the space between them. It is in one orbit, and then it is in the other, with no path, no motion, no in-between moment, where it is somewhere along the way. The gap is not crossed. It is simply skipped. As strange as this was, it worked, and it worked with a precision that silenced doubt. For decades, scientists had known that each chemical element, when heated, gives off light only at certain sharp, specific colours, a fixed pattern of bright lines, like a barcode unique to that element. Nobody knew why. Bohr's model explained it perfectly. The sharp lines are the photons emitted as electrons jump between the allowed energy levels, and since the levels are fixed, the colours are fixed. For hydrogen, the simplest atom, Bohr's formula predicted the exact pattern of lines that had been measured, matching the known results to extraordinary accuracy. A wild set of assumptions that nobody could justify produced numbers that were exactly, undeniably right. It is worth lingering on those spectral lines, because they are one of the most useful gifts quantum physics ever gave us, and they turn the abstract idea of energy levels into something you can almost hold in your hand. Every element has its own unique set of allowed electron jumps, and therefore its own unique pattern of coloured lines, a fixed signature, as individual as a fingerprint. Hydrogen has its pattern, helium another, sodium another still. And because these patterns are set by the unchanging structure of the atom, they are the same everywhere in the universe. When astronomers spread out the light of a distant star or galaxy into its colours, they find these same patterns of lines printed into it, and from them they can read what that faraway object is made of, how hot it is, and even how fast it is moving toward us or away. The light of a star that left its source millions of years ago still carries, in its pattern of lines, a faithful record of the quantum jumps happening in atoms across the galaxy. Helium itself, was discovered in the light of the sun before it was ever found on Earth, identified by a line in the solar spectrum that matched no known element. Bohr's strange little jumps, the ones that seemed to make no physical sense, turned out to be the alphabet in which the whole universe spells out what it is made of. We read the cosmos by the light of electrons leaping between forbidden steps. This is the pattern tightening again, the same one we saw with Planck. A physicist is forced to assume something that makes no physical sense: energy in lumps, orbits that do not radiate, electrons that teleport between levels, and the universe rewards the nonsense with perfect agreement. Bohr knew his model was provisional and strange. It worked beautifully for hydrogen and struggled with heavier atoms, and he never pretended it was the final word. But it had established something that could not be walked back. The inside of the atom is quantized. It runs on discrete steps and sudden jumps, not smooth motion. The building block of all matter does not obey the rules of the solid world it builds. And buried inside the quantum jump was a question that nobody could yet answer, a question that would become one of the most unsettling in all of physics. Consider a single electron sitting in a higher orbit, ready to drop. When exactly will it jump? Bohr's theory could tell you the odds. It could say that over a certain stretch of time, a jump becomes likely, but it could not tell you the moment. Take two identical atoms in identical states, and one might emit its photon now, the other an hour from now, with nothing whatsoever to distinguish them, nothing in either atom that determines which will go first. The timing of the jump appeared to be, at bottom, a matter of pure chance, not chance born of our ignorance of some hidden mechanism, but chance with no mechanism underneath it at all. At the time, this was easy to set aside as a temporary gap, a detail to be filled in later. It was not a gap. It was the first clear sight of the thing this whole story is about. The universe, at the level of the atom, does not appear to decide in advance. Bohr's allowed orbits left one obvious question hanging. Why these orbits and not others? What could possibly single out one staircase of energies as permitted and forbid everything in between? The answer, when it came, would be the strangest reframing yet. A French aristocrat was about to suggest that the reason electrons are picky about their orbits is that electrons, like light, are not really particles in any simple sense. They are waves. And once matter itself turned to waves, the solid world had nothing left to stand on. Part 5. When matter became a wave. The idea that finally explained Bohr's mysterious orbits came not from a laboratory, but from a French aristocrat asking a simple, symmetrical question. His name was Louis de Broglie, and in his 1924 doctoral thesis, he turned Einstein's logic around and pointed it in the opposite direction. Einstein had shown that light, which everyone had treated as a wave, also behaves as a stream of particles. De Broglie asked the obvious mirror-image question that somehow no one had taken seriously. If waves can act like particles, then why shouldn't particles act like waves? Why shouldn't an electron, which everyone pictured as a tiny solid speck, also have a wavelength, a spread-out, rippling nature of its own? It was the kind of question that sounds almost too neat to be true, and his thesis committee was unsure what to make of it until Einstein himself read the work and pronounced it sound. De Broglie put a precise number on the idea. Any object, he said, has a wavelength equal to Planck's constant divided by its momentum roughly, divided by its mass times its speed. Because Planck's constant is so unimaginably small, the wavelength of any everyday object is far too tiny to ever notice. A thrown baseball, a walking person, a drifting dust grain, all have wavelengths so minuscule that no experiment could ever detect their wave nature, which is exactly why the world looks solid and particle-like to us. But an electron is so light, its momentum so small, that its wavelength comes out comparable to the size of an atom itself. At that scale, the wave nature of matter is not a rounding error. It is the whole story. And suddenly Bohr's arbitrary orbits made sense. If an electron circling a nucleus is really a wave, then only certain orbits will work, the ones where the wave comes back around and meets itself smoothly, closing into a whole number of wavelengths, like a vibrating guitar string that can only hold certain pure notes. An orbit where the wave failed to close would interfere with itself and cancel out. The allowed energy levels that Bohr had simply declared into existence now fell out naturally, as the only orbits where the electron wave could form a stable, standing pattern. The staircase of energies was not arbitrary after all. It was music, the set of notes a confined electron wave is able to play. A few years later, the prediction was confirmed directly when electrons fired at a crystal came out the other side in the spread-out interference pattern that only waves produce. Matter diffracts. The solid speck was a wave all along. This is the moment the comforting mental picture truly dissolves. Up to now, you could still imagine the electron as a tiny ball, even a strange ball that jumps between orbits. After de Broglie, even that is gone. The electron is a spread-out, rippling thing with no definite size and no single location, smeared around the nucleus like a standing wave of pure possibility. And if that is true of the electrons in a hydrogen atom, it is true of the electrons in every atom in your body, every atom in the chair, every atom in the floor. The solidity you feel is the touch of one cloud of waves pressing against another. There is no little ball anywhere underneath it. There never was. The next step was taken by a young man who decided to stop trying to picture the atom at all. Werner Heisenberg was just 23 years old, brilliant, ambitious, and in the early summer of 1925, miserable with hay fever. The pollen of late spring had swollen his face so badly he could barely work, and so he asked for leave and travelled to a place where there was nothing to make him sneeze. He went to Helgoland, a small, rocky, treeless island far out in the North Sea, scoured by wind, almost bare of plant life. There, alone, with his symptoms easing and nothing to distract him, he attacked the problem of the atom in a completely new way. Heisenberg made a radical decision. He gave up entirely on the idea of picturing what the electron is doing, its orbit, its path, its position from moment to moment. None of that, he reasoned, is ever actually observed. What we observe are the frequencies and the brightnesses of the light the atom emits, the lines in the spectrum. So he resolved to build a physics out of only those observable quantities, and to refuse to talk about anything he could not measure. He arranged the observable numbers into tables and found the rules for combining them, and out of this strange, abstract bookkeeping, a complete and consistent mechanics emerged. With the help of his mentor Max Born and their colleague Pascal Jordan, it was soon recognized that Heisenberg's tables were mathematical objects called matrices, and the theory took the name matrix mechanics. It was the first full, self-consistent theory of the quantum world. Picture the moment it broke open. It is the middle of the night, near 3 a.m, on Helgoland. Heisenberg sits hunched over his calculations by lamplight, the wind off the North Sea pushing at the windows, his swollen eyes finally clear enough to work. He is checking whether his strange new scheme respects the conservation of energy, whether the numbers will balance or fall apart. Term by term, the calculation comes out right. The energy holds. The new mechanics is consistent. He is so agitated by what he is seeing that he keeps making arithmetic mistakes from the excitement, and when at last it all fits together, he is far too stirred to sleep. He has the feeling, he later wrote, of looking through the surface of atomic phenomena to something strange and beautiful underneath, and he feels almost dizzy at the thought that he now has to follow this new physics wherever it leads. In the grey light before dawn, he leaves the house, walks to the southern tip of the island, and climbs a rock that juts out over the sea, and there he waits for the sun to come up over the water. A 23-year-old has just written down the machinery of a new reality, alone on a barren island, and the only witness is the sunrise. What makes that night on Helgoland so haunting is that Heisenberg could not really picture what he had made. He had built a working description of the atom by deliberately refusing to imagine the atom, by treating the electron's path, its position, its orbit as meaningless questions, and keeping only the numbers that experiments could actually yield. It worked, and that was almost the unsettling part. A theory that declined to say what was happening underneath nevertheless predicted, correctly, what would be observed on the surface. Heisenberg later said that in those first hours he felt almost afraid, as though he had been allowed to look at something he was not sure he had any right to see. He was not describing the simple thrill of a tidy solution. He was describing the vertigo of discovering that the most successful way to talk about the atom was to stop talking about what the atom actually is. That refusal, the decision to predict the results and stay silent about the picture, would harden, over the next few years, into the official attitude of the new physics, the very attitude that would so enrage Einstein. It began here, with an exhausted young man on a rock above the North Sea, who had found a door and was no longer sure he wanted to know what lay on the other side of it. There was one feature of Heisenberg's new mathematics that seemed like a small technicality at the time and turned out to be the beating center of everything. In ordinary arithmetic, the order in which you multiply two numbers does not matter. 3 times 5 is the same as 5 times 3. But in Heisenberg's scheme, the quantities standing for things like an electron's position and its momentum did not obey that rule. Multiply them in one order and you got one answer. Multiply them in the other order and you got a different one. The two operations did not commute, as mathematicians say. At first this looked like an odd quirk of the formalism. In fact, it was the universe whispering its most important secret in a language no one yet knew how to read. The failure of position and momentum to commute would soon be revealed as something staggering, a statement that a particle cannot have a definite position and a definite momentum at the same time, not because we cannot measure them, but because it does not have them. The order of multiplication mattered because the questions interfere with each other. But that revelation was still 2 years away, and it would arrive in the form of a principle that bears Heisenberg's name to this day. Notice how far the solid world has fallen by now. In 25 years, energy has become grainy. Light has become particles that are also waves. The atom has become a thing of forbidden gaps and impossible jumps. And now matter itself, the electron at the base of everything, has turned into a spread-out wave with no definite place. A young man on an island has built a working theory of all this by refusing, on principle, to imagine what any of it looks like. The pieces are nearly all on the table. What is still missing is the single idea that ties them together and tells us what they mean. The idea that the wave de Broglie discovered and the matrices Heisenberg wrote are not describing where a particle is, but only the chances of where it might be found. That idea arrived in 1926, from a different direction entirely, and when it did, it brought chance into the foundation of physics and never let it leave. Part 6. The day chance entered the equations. In 1926, an Austrian physicist gave the quantum world a far gentler face, and then watched in dismay as that face revealed the most disturbing idea of all. His name was Erwin Schrödinger, and he disliked Heisenberg's matrices intensely. He found them abstract, ugly, impossible to picture, a physics that refused to say what was actually happening. So he built an alternative. Taking de Broglie's idea that matter is made of waves, Schrödinger wrote down an equation now, one of the most important in all of science, that describes how such a wave moves and changes over time. The wave itself, he wrote, with the Greek letter psi, and the equation tells you, given the wave now, exactly what the wave will be doing at any moment in the future. Crucially, this evolution is perfectly smooth and perfectly predictable. There are no jumps in Schrödinger's equation, no sudden discontinuities, just a wave flowing and reshaping itself in a continuous, lawful way. Physicists were enormously relieved. Here, at last, was a quantum theory you could draw that ran on familiar wave mathematics and that did not require electrons to teleport. Within months, it was shown that Schrödinger's wave mechanics and Heisenberg's matrix mechanics, which looked nothing alike, were in fact mathematically identical, two different languages describing the very same theory. Most physicists happily adopted Schrödinger's version because it was so much easier to visualize and calculate with. But beneath the relief, a question was waiting, and it was the question that mattered most. Schrödinger had given everyone a beautiful wave. He had not been able to say what the wave actually is. What is it that is waving? Schrödinger himself badly wanted the answer to be simple and physical. He hoped his psi wave was a real, tangible thing spread out in space, that the electron was not a particle at all, but literally a smeared cloud of electric charge rippling around the nucleus. For a little while this dream looked possible, but it broke down quickly. For one thing, the wave for a system of several particles does not live in ordinary three-dimensional space at all. It lives in an abstract space of many dimensions, which no real physical substance could occupy. For another, whenever you actually go looking for an electron, you never find a smeared-out cloud. You find a whole, point-like electron in one place. The wave might be spread across a room, but the electron, when detected, always shows up complete and localized, here and not there. A real, physical wave of matter could not do that. So, if the wave is not the electron itself, then what is it? The answer came from Max Born, the same Born who had helped Heisenberg, and it is the true turning point of this entire story. The wave, Born proposed, is not a wave of matter or charge. It is a wave of probability. The value of the wave at a given place, when you square it, tells you the chance of finding the particle at that place if you look. Where the wave is large, the particle is likely to be found. Where the wave is small, it is unlikely. Where the wave is zero, the particle will never appear. The psi wave does not tell you where the electron is. The electron is not anywhere in particular until you look. The wave tells you only the odds of each possible result. Born received the Nobel Prize for this single insight, though not until 1954, almost 3 decades later, a measure of how long it took the world to absorb what he had done. Sit with what this claim actually says, because it is easy to let it slide past as a technical detail, and it is not a technical detail. It is a statement that the most fundamental description we have of a particle is a description of chances, not facts. Before you measure, the theory does not secretly know where the electron is and decline to tell you. The theory contains only probabilities, all the way down, and the deciding evidence, gathered over the following decades, indicates that this is not a limitation of the theory, but a feature of the world. The electron genuinely does not have a definite position waiting to be uncovered. It has a set of potential positions, each with its odds, and the single actual position comes into being only at the moment of measurement. This is the blur from the very beginning of our story, now written into the central equation of physics. Reality, underneath, is not a list of facts, it is a list of likelihoods. It is worth being very clear about how this kind of chance differs from the ordinary chance we meet every day, because the difference is the whole point. When you roll a die, the outcome feels random, but physics had always assumed it is not truly random at all. The die obeys exact laws. If you knew the precise force of the throw, the spin, the friction of the table, the faint currents in the air, you could in principle calculate the result with certainty. The randomness of the die is only a measure of our ignorance, a gap in our information, exactly as Laplace had said. For 3 centuries, every probability in physics had been this comfortable kind, a confession of what we did not happen to know about a world that was itself perfectly definite. Born's probability is a different creature entirely. The quantum wave does not conceal a definite answer that we are merely too ignorant to see. The evidence indicates there is no hidden answer underneath at all. The particle does not secretly possess a position that the probability only estimates. The probability is the whole of the story, the most complete description that exists. This is the move that broke Einstein's universe. He could accept probability as a tool for managing ignorance. He could not accept that probability went all the way down, that the universe itself did not know where the particle was, that the dice were not loaded by hidden causes but genuinely, irreducibly blank until thrown. And that, precisely, is what Born had proposed, and what the following century of physics would confirm. One man saw exactly what this meant, and refused with everything in him to accept it. Albert Einstein had spent his life believing that the universe is lawful, orderly, and real, independent of observation, that there is a definite world out there, obeying definite rules, whether or not anyone looks. Born's probability wave told him the opposite, that at bottom the universe runs on chance, and Einstein found the idea intolerable. In December of 1926, he wrote a letter to Born that would become the most famous single sentence in this whole debate. Quantum theory, he admitted, was impressive and useful, but he was sure it was not the final truth. The theory, he wrote, yields a great deal, but it hardly brings us closer to the secret of the old one, his name for the deity, for the underlying order of nature. And then the line that has defined the resistance ever since. I, at any rate, am convinced that he does not play dice. God does not play dice. Hold on to that sentence, because we are going to hear it again, and the second time it will mean something very different. To Einstein in 1926, it was a statement of faith and of hope, a conviction that the randomness of quantum mechanics had to be a temporary appearance, a sign that the theory was incomplete, that some deeper layer of definite, orderly reality must lie beneath it, still waiting to be found. He was not denying that the theory worked. He was insisting that its dice rolling could not be the last word about a rational universe. For the next 30 years, he would search for the hidden order beneath the dice, and he would die still searching. The tragedy, which we will reach in time, is that the universe was eventually asked the question directly, with an experiment, and it answered against him. For now, simply notice where we have arrived. The solid world began this story as a machine of definite parts. It has become a wave of probabilities, governed by an equation that predicts only odds. Everything works. This probabilistic physics is what gives us the laser, the computer chip, the medical scanner, the entire modern world, and it predicts the behavior of matter to a precision no other theory has ever matched. But the price of that success is the loss of the most basic comfort there is. The particles you are made of do not sit in definite places between measurements. They wait, as clouds of chance, for the world to ask them where they are. And the next discovery, just 1 year later, would show that this is not a gap to be filled, but a wall that can never be climbed. There is a limit built into the universe itself on how much of reality can ever be made definite at once. And it has a name. Part 7. The limit built into everything. In 1927, Heisenberg returned to the quirk in his mathematics, the one where the order of multiplication changed the answer, and he uncovered what it had been trying to tell him. It was a limit woven into the fabric of reality on how much you are allowed to know. The principle is now called the Heisenberg uncertainty principle, and it concerns pairs of quantities that are linked in a particular way, most famously a particle's position and its momentum which is its mass times its velocity. The principle says that these two properties can never both be sharp at the same time. The more precisely a particle's position is defined, the more hopelessly blurred its momentum becomes, and the more precisely its momentum is defined, the less its position means anything at all. There is a hard flaw on the product of the two uncertainties. A flaw set, once again, by Planck's constant. You can trade one for the other, sharpening the position by smearing the momentum or the reverse, but you can never push both below that limit together. Nature simply will not allow a particle to possess a perfectly definite place and a perfectly definite motion at the same instant. It is easy to hear this and reach for a comfortable misreading, so let us close that door now, because the misreading is the single most common mistake people make about quantum physics. You might think the uncertainty is just a practical problem of measurement, that to see a particle you have to bounce light off it, and the light gives it a kick, so the act of measuring disturbs the thing being measured. There is a grain of truth in that image, and Heisenberg himself first reached for it, but it is not what the principle actually means, and it is misleading in a way that hides the real strangeness. The uncertainty is not about the clumsiness of our instruments. It is not that the particle has a definite position and momentum, which our measurement unfortunately blurs. It is that the particle does not have a definite position and momentum at the same time to begin with. There is nothing there to disturb. The sharp values we want to find are simply not present in the world until one of them is forced into being by a measurement, and the very act of forcing one makes the other meaningless. The limit is not in the microscope. It is in reality. This is the same truth we keep arriving at from new directions. Planck found energy comes in grains. Born found the wave is made of odds. Now Heisenberg finds that the basic properties of a particle cannot all be definite at once. They are different faces of one fact. The world, at its base, is not a collection of things with settled properties. It is a haze of possibilities that only ever offers up part of itself, and only when asked. And there is no experiment, no matter how clever, no matter how advanced, that will ever get around the limit, because the limit is not a failure to see what is there. It is the world declining to be more definite than it is. Nowhere does this come through more clearly, or more hauntingly, than in a single experiment that the physicist Richard Feynman would later call the one true mystery of quantum mechanics, the experiment that holds the whole of its strangeness in one image. It is called the double-slit experiment, and it is simple enough to picture completely. Imagine a darkened room. On one side, there is a device that fires electrons, one at a time, toward a barrier. In that barrier, there are two narrow slits, side by side, both open. Beyond the barrier is a screen that records a small dot wherever an electron lands. Now you wait and you watch. The first electron leaves the gun, crosses the gap, and somewhere on the screen a single dot appears. Then a long pause, and another electron, another dot, somewhere else. The electrons are leaving the gun one by one, with so much space and time between them that no electron could possibly be interacting with another. Each one travels the room alone. Each one strikes the screen as a single, localized point, exactly as a tiny particle should. And for a while, the dots seem scattered, almost random, with no pattern you can name. You keep watching. Over an hour, over a night, the dots accumulate, thousands of them, then millions. And slowly, out of all those separate, lonely impacts, a pattern assembles itself on the screen, not two bright bands behind the two slits, as you would expect from little bullets passing through, but a series of many stripes, bright bands and dark bands, alternating across the screen. That striped pattern is an interference pattern, and it is the unmistakable signature of waves. It is what you get when two waves overlap, reinforcing each other in some places and cancelling in others. But there were never two waves. There was only one electron at a time crossing the room alone. Each single electron, it seems, somehow went through both slits at once, interfered with itself, and landed according to the odds set by that self-interference. The pattern was hidden inside the probabilities all along, and it took millions of single particles to reveal it. Now comes the part that should make the hair on your arms lift. You decide you want to know the truth. You place a tiny detector at the slits, a device that simply registers which slit each electron actually passes through. You are not blocking anything. Both slits stay open. You are only watching, only asking the question, which way did it go? And the instant you do, the striped interference pattern vanishes. The electrons begin landing in just two plain bands, one behind each slit, exactly as ordinary particles should. The wave-like behavior is gone. The moment you force each electron to commit to a definite path through one slit or the other, it stops being a spread-out wave of possibility and becomes a particle with a single history. Turn the detector off, stop asking the question, and the stripes return. The electrons go back to passing through both slits at once. The world behaves one way when you look at the path, and another way when you do not. This is the blur sharpening under your gaze, made visible in a laboratory. When you do not ask which slit, the electron has no definite path. It is genuinely both routes at once, a wave of possibility that interferes with itself. When you do ask, the universe is forced to give a definite answer. The possibility collapses to a single path, and the interference, which depended on the electron not having a definite path, simply disappears. The act of acquiring the information changes what happens, not because the detector is clumsy or gives the electron a knock, but because before the measurement there was no fact about which slit, and the measurement creates one. You are not discovering a hidden answer. You are forcing the world to choose. It was to make sense of this that Bohr offered his own guiding idea, which he called complementarity. The wave nature and the particle nature of something like an electron, Bohr said, are two complementary aspects of a single reality. They are both true, but they can never be seen at the same time, because the kind of experiment that reveals one necessarily hides the other. Ask about the path, and you see particles. Ask about the pattern, and you see waves. There is no single experiment and no single picture that shows you both at once, because the world does not contain both at once. Which face of reality appears depends on the question you choose to put to it. Reality, on this view, is not a finished thing you are observing from outside. It is something that takes shape, in part, according to how you interrogate it. Step back and feel the size of what has been established by the end of 1927. In a single generation, physics has discovered that energy is grainy, that light and matter are both waves and particles, that the most fundamental description of a particle is a wave of pure probability, that position and momentum cannot both be definite at once, and that the simple act of looking changes what is real. The steadiness you trust in the world around you is, at the smallest scale, the universe choosing to give definite answers only when forced, and remaining a haze of maybes the rest of the time. The floor beneath your certainty has not just cracked. It has revealed itself to have been a kind of agreement all along, an answer the universe supplies on demand rather than a fact it was keeping in storage. No one understood the weight of all this better, or resisted it harder, than Einstein. He was not a man to mistake the theory for a passing fashion. He could see it was powerful, and probably correct as far as it went. But he was certain it could not be complete. There had to be, he believed, a deeper layer of definite reality hidden beneath the quantum haze, a set of real facts that the theory was simply failing to capture. And in the autumn of 1927, the founders of the new physics gathered in one room in Brussels, and Einstein arrived ready to fight for the solid world. What followed was one of the great intellectual duels in the history of science, a long argument between two friends that neither would ever fully win, and that would not be settled for another half a century. Part 8. the argument that never ended. In October of 1927, the greatest collection of physicists ever gathered in one place came together in Brussels, and they spent much of the meeting arguing about whether reality is real. The occasion was the fifth Solvay conference, devoted to electrons and photons, and the guest list is almost difficult to believe. 29 physicists attended, and 17 of them either already held or would go on to receive the Nobel Prize. Einstein was there, and Bohr, and Planck, the reluctant grandfather of the whole affair. Marie Curie was there, the only woman in the room and already a holder of 2 Nobel Prizes in 2 different sciences. The young revolutionaries were there in force: Heisenberg, Schrödinger, Dirac, Pauli, de Broglie, and Born. The group photograph taken at that meeting has been called, only half in jest, the most intelligent photograph ever taken. Nearly everyone who built the quantum revolution sat together for that picture, and the disagreement captured in their faces had not been resolved when they stood up again. By this point, a particular way of understanding quantum mechanics had taken shape, largely around Bohr in Copenhagen, and it came to be called the Copenhagen interpretation. It would dominate physics for the rest of the century. Its claims were stark. The wave function is the complete description of a system there is no hidden, more detailed reality underneath it. A particle does not possess definite properties, like position, until it is measured. The measurement does not reveal a pre-existing value, but brings a definite value into being. And as for what the particle is doing between measurements, when no one is looking, the Copenhagen answer was essentially that the question has no meaning. Do not ask. The theory predicts what you will see when you measure, and that is all there is and all there can be to say. To Bohr and his circle, this was not a failure of the theory. It was the theory finally being honest about the kind of world we live in. To Einstein, it was close to a betrayal of everything physics was for. He could not accept that there is no definite reality between observations, that the universe only sharpens into fact when someone looks. So at Solvay he went on the attack, and the form the attack took has become legendary. Picture the rhythm of those days. It is morning in the dining room of the hotel in Brussels. Einstein comes down to breakfast, relaxed, almost cheerful, and sets before Bohr a freshly invented thought experiment, an imaginary, perfectly arranged apparatus that he claims would let you measure 2 things at once, that the uncertainty principle says you cannot or otherwise slip past the limits of the new physics. Bohr listens, and the colour drains from his face. He cannot see the flaw immediately, and the possibility that Einstein is right is intolerable. All day, Bohr carries the puzzle with him, muttering, pacing the halls, turning it over with anyone who will listen, scarcely able to eat. And by dinner, again and again, he has found it the hidden mistake in Einstein's reasoning, the overlooked detail that rescues the uncertainty principle and the whole quantum edifice. Each morning, Einstein builds a trap. Each evening, Bohr escapes it. Neither man yields an inch. The most famous of these duels came a few years later, at the next Solvay meeting in 1930, and it shows just how far Einstein was willing to reach. He proposed what is now called the photon box. Imagine a box full of light with a shutter over a small hole and a clock inside that opens the shutter for the briefest instant, letting exactly 1 photon escape at a precisely known moment. So far, the time of the photon's escape is pinned down sharply. Now, Einstein said, weigh the box before and after. Since energy has mass, by his own famous relation between the two, the tiny change in the box's weight tells you exactly how much energy the photon carried. You would then know both the precise time of emission and the precise energy, 2 quantities the uncertainty principle insists, cannot both be sharp. The uncertainty principle would be broken, and with it the claim that the quantum description is complete. Bohr was, by all accounts, devastated. He spent a sleepless, anguished night, and by the next morning he had the answer, and the answer was exquisite. To weigh the box, you must let it move, ever so slightly, in the field of the Earth's gravity. And, according to Einstein's own general theory of relativity, a clock changes its rate depending on its position in a gravitational field. The very act of weighing the box to measure the photon's energy disturbs the clock that measured the time by precisely the amount needed to restore the uncertainty principle. Bohr had defeated Einstein's attack using Einstein's own greatest creation. Gravity itself stood guard over the quantum limit. There is something genuinely moving in this long contest, and it is worth slowing down to feel it, because it is the human center of our whole story. Einstein and Bohr were not enemies. They admired each other enormously, even loved each other in the particular way of two people locked in an argument that matters more to them than almost anything else. They were the two greatest physicists of their age, and they spent decades unable to convince each other of the one thing each held most certain. Bohr was so haunted by the argument that, the story goes, he was still mentally debating Einstein on the last night of his own life, drawing Einstein's photon box on his blackboard the very day before he died. More than 30 years later, Einstein, for his part, never stopped believing his old friend was missing something essential about reality. Two brilliant, honest people who respected each other completely, looked at the same equations and the same experiments, and could not agree on whether the world is definitely there when no one is watching. That is how hard this question is. It is not hard because anyone involved was foolish. It is hard because it may be the hardest question there is. There is a third figure in these debates, whose anguish captures the human cost better than anyone's. Paul Ehrenfest was a gifted physicist and a close friend of both Einstein and Bohr, and at the Solvay meetings he found himself caught painfully between them. He admired Einstein beyond almost anyone alive, and yet, as he watched the arguments unfold, he came to believe that Bohr was right and Einstein was wrong, that his hero was making the same kind of stubborn, losing stand against new physics that an older generation had once made against Einstein's own relativity. Ehrenfest was reportedly reduced nearly to tears, torn between loyalty to his friend and his honest reading of the physics, telling Einstein with real sorrow that he was sorry, but he simply could not side with him any longer. To watch the person you admire most refuse to accept what the evidence is saying, and to have to stand against him is its own kind of quiet grief, and it played out in the margins of these famous debates. The quantum revolution did not only overturn the physics of solid objects, it divided friendships, and it asked people to choose between the thinkers they loved and the conclusions they could not honestly deny. After the photon box, Einstein changed his strategy, and the change is important. He had spent years trying to prove the uncertainty principle wrong, to show that you could beat the limits directly, and Bohr had defeated him every time. So Einstein gave up that line of attack. He conceded that quantum mechanics, as far as it went, was correct, that its predictions held and its limits could not be cheated. But correct, he insisted, is not the same as complete. A theory can make perfect predictions and still be missing part of the picture. And so Einstein set out to show not that quantum mechanics was wrong, but that it was incomplete, that beneath its probabilities there had to be a deeper layer of definite, real facts that the theory simply failed to include. To make that case as sharply as possible, in 1935 he constructed, with two younger colleagues, the most penetrating argument of his entire campaign against the quantum world. It would take physics 30 years to answer it, and the answer, when it finally came, would be nothing he could have wanted. Part 9. Einstein's Last Stand. In 1935, Einstein and two younger physicists published a short paper with a question for a title: Can the quantum mechanical description of physical reality be considered complete? Their answer was no, and the argument they built to prove it accidentally uncovered the strangest phenomenon in all of physics. The paper is known by the initials of its three authors, Einstein, Boris Podolsky, and Nathan Rosen, as the EPR paper. Its strategy was clever. Instead of attacking the uncertainty principle head-on, which had failed, Einstein used the theory's own rules to push it toward what he saw as an absurd conclusion. The setup involves two particles that interact and then fly far apart. Because they once interacted, quantum mechanics describes them as a single linked system, their properties tied together even as the distance between them grows to meters, kilometers, light years. Whatever happens to one is bound up with the other. Here is the trap Einstein laid. Suppose you measure some property of the first particle, say its position. Because the two particles are linked, your result instantly tells you the corresponding property of the second particle far away. You did not touch the second particle, you did not go near it, yet the moment you measured the first, the second's matching property became known. Now, said Einstein, there are only two possibilities, and you must choose. Either your measurement here somehow reached across all that distance and instantly forced the far particle to take on its value, an influence travelling infinitely fast, which Einstein dismissed as spooky action at a distance and considered plainly impossible, since nothing should outrun light. Or else the far particle had that property all along as a definite fact from the moment the two separated, and your measurement merely let you infer it. Einstein found the second option obviously correct. But quantum mechanics says the far particle had no definite property until measured. So if the property was real all along, and to Einstein it clearly was, then quantum mechanics is leaving something out. It is incomplete. There must be hidden variables, definite real properties carried by each particle that the theory fails to describe. It was, on its face, a powerful argument, and it rested on an assumption almost too obvious to state, that two objects far apart are separate, that what you do here cannot instantly change what is true there. Physicists call this assumption locality, and it is woven into our entire sense of how the world works. Things influence their neighbours. Effects travel from place to place at finite speed. A measurement in one city does not reach out and arrange matters in another in the same instant. Einstein was so sure of locality that he was willing to use it to convict quantum mechanics of being incomplete. If holding on to a definite, local reality meant the celebrated new theory had a hole in it, then so much the worse for the theory. The linked behaviour at the centre of the EPR argument so startled Erwin Schrödinger that he gave it the name it still carries. Writing in response that same year, he called it entanglement, and he did not consider it one strange feature among many. He called it the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. Two entangled particles do not simply each carry their own hidden marching orders. They share a single, indivisible quantum state that stretches across whatever distance separates them, so that neither has its own definite properties, only the pair, taken together, has a definite relationship. Measure one, and the whole shared state resolves at once, fixing the other in the same breath. Schrödinger saw clearly that this was the most radical break with the old physics, and the hardest to swallow, and he was not at all sure he could swallow it himself. In that same remarkable paper, Schrödinger gave the world its most famous image of quantum strangeness, and he meant it not as a celebration, but as a protest. He asked you to imagine a cat sealed in a steel box, along with a small, fiendish apparatus. Inside the box is a tiny amount of a radioactive substance, so little that over the course of an hour there is an even chance that one atom decays and an equal chance that none does. If an atom decays, a detector trips a hammer that shatters a flask of poison and the cat dies. If no atom decays, the poison is never released and the cat lives. Now, Whether a radioactive atom decays in a given hour is a purely quantum event, governed by nothing but probability, exactly the kind of undecided, blurred situation we have been describing all night. Quantum mechanics, taken literally, says that until the box is opened and observed, the atom is in a combination of decayed and not decayed at once. And since the cat's fate is chained to the atom, the theory says the cat, too, is in a combination of states alive and dead at the same time, a smear of both possibilities, until someone lifts the lid and looks. Schrödinger's point was that this is ridiculous. A single atom being in two states at once is one thing. We cannot see it directly, so we can almost tolerate it. But a cat is not invisible. A cat is a living creature the size of your two hands, and the idea that it hangs in some blurred mixture of life and death until a human being checks is, on its face, absurd. Schrödinger built the thought experiment to drag the strangeness out of the safe darkness of the atom and into the daylight of the everyday, where its oddness could not be ignored. He was asking the unanswered question at the center of everything. If quantum objects have no definite state until measured, and the world is built entirely of quantum objects, then why does the large world around us look so stubbornly definite? Where, exactly, does the blur end and the solid world begin? What counts as a measurement, and why does a cat seem to count, but a single atom does not? That question is called the measurement problem, and nearly a century later, it remains unsolved. The cat is not a quaint old puzzle. It is a wound in the theory that has never closed. There is a strange irony in what became of Schrödinger's cat, and it is worth noting before we move on. Schrödinger invented the cat to ridicule the theory, to show that taking quantum superposition seriously at the everyday scale led straight into nonsense. He expected people to recoil from the absurdity and conclude that something must be missing from the standard story. Instead, the cat slipped his control and became the single most beloved image in all of quantum physics, printed on posters and shirts, invoked in films and cartoons, repeated by people who have no idea it was meant as an objection. The protest became the mascot. And the reason it endures is that the absurdity Schrödinger pointed at has never actually been resolved. We still cannot say, in any agreed-upon way, why a single atom can be in two states at once, while a cat cannot, or where exactly the line falls between the blurred quantum world and the definite everyday one. Schrödinger built a trap to catch the theory in an absurdity, and the theory simply sat down inside the trap and has lived there ever since, a cat that is somehow still, after 90 years, neither quite alive nor quite dead in the minds of the physicists who keep arguing about it. Notice that Einstein, in this final phase, was not denying the strangeness. He was clinging to a last hope. If the EPR argument was right, then the particles really did carry definite properties all along, hidden from the theory but present in the world, and the dreadful randomness of quantum mechanics would be only a surface appearance, a fog over an orderly, definite reality underneath. God would not be playing dice after all. The dice would be a trick of our limited view. This was the form Einstein's faith now took. Not that quantum mechanics was wrong, but that a deeper, calmer, fully real world was waiting to be found beneath it. It was a beautiful hope, and an entirely reasonable one, and for 30 years there seemed to be no way on Earth to test it. The disagreement between Einstein and Bohr looked like pure philosophy, a matter of taste about which no experiment could ever decide. The kind of question physicists set aside as unanswerable and got on with their calculations. Then, in 1964, a quiet physicist from Northern Ireland, working alone on a problem almost everyone else considered a waste of time, found the thing that everyone had assumed could not exist. He found a way to take the argument between Einstein and Bohr, the question of whether reality is definite and local, or genuinely undecided until measured and turn it into a number you could measure on a laboratory bench. He made the unanswerable answerable, and the universe was about to be asked, directly, whether Einstein or Bohr had been right. Part 10. The Man Who Made It Testable. For almost 30 years, the question of whether Einstein or Bohr was right sat in a strange limbo. Everyone agreed quantum mechanics made the correct predictions. Whether there was a hidden, definite reality underneath those predictions seemed to be a matter of personal taste, a philosophical preference no experiment could settle. Then a physicist named John Stuart Bell proved that everyone had been wrong about that, not about quantum mechanics, but about the question itself being untestable. Bell was from Belfast, in Northern Ireland, the son of a working-class family, and by the 1960s he was employed at CERN, the great European physics laboratory, designing particle accelerators. The foundations of quantum mechanics were not his job. They were his passion, pursued in his own time, and he approached them with a sympathy that is important to understand. Bell was, by inclination, on Einstein's side. He found the Copenhagen insistence that nothing is definite until measured to be vague and unsatisfying, and he hoped that Einstein's intuition was right, that a deeper, definite, local reality could be found beneath the quantum fog. He set out not to defeat Einstein, but, if anything, to give his hidden variable dream a fair and rigorous hearing. What he found instead changed everything, including his own hopes. Bell asked a precise question. Suppose Einstein was right, and entangled particles really do carry definite, hidden instructions with them from the moment they separate a complete set of pre-arranged answers for any measurement that might be made, with no faster-than-light influence allowed between the two distant particles. Suppose, in other words, that reality is both definite and local, exactly as Einstein wanted. If that were true, Bell asked, what would the experimental results actually look like over many, many runs? And he discovered something nobody had noticed in 30 years of arguing. A world of definite, local, hidden instructions is not free to produce any pattern of results it likes. It is bound by a mathematical limit. If you measure your entangled particles at a variety of different settings and tally how often the distant results agree, then in any local hidden variable world, a certain combination of those agreement rates can never climb above a fixed value. This ceiling is now called a Bell inequality. Einstein's universe, whatever its hidden details, must respect it. Then Bell calculated what quantum mechanics predicts for the very same measurements, and quantum mechanics breaks the limit. For certain choices of settings, the theory says the distant particles will agree more often and more tightly than any local hidden variable scheme could ever allow. The correlations are simply too strong, too coordinated, to be explained by particles carrying preset instructions and never communicating. This was the breakthrough. The two views of reality, Einstein's definite, local world and the quantum world of genuine indefiniteness, no longer made the same predictions. They made different predictions about a specific number you could measure on a laboratory bench. The argument that everyone had filed away as unanswerable philosophy had a definite, experimental answer hiding inside it all along. You only had to do the experiment. It helps to feel why the quantum correlations are so impossible to fake with hidden instructions. Imagine two people sent to opposite ends of the earth, each handed a sealed envelope, and each asked, at the last moment, one of several possible questions. If the envelopes contain pre-written answers, fixed before the two people parted, then there are limits to how cleverly their answers can be made to match across the full range of possible question combinations. You can arrange for them to agree perfectly on some pairings, but only at the cost of agreeing less on others. The pre-written cards cannot be coordinated past a certain point without the two people being able to talk to each other. That ceiling is the Bell inequality. Entangled particles sail straight past it. They agree more often, across the full range of settings, than any set of sealed envelopes possibly could, as if the two particles were somehow still consulting each other at the moment of measurement, even with no time for any signal to pass between them. There are no pre-written cards strong enough to imitate what entangled particles actually do. The setting that each experimenter chooses is, in practice, the angle of a measuring device, the orientation at which each distant detector is set to question its particle. When the two angles happen to match, entangled particles agree perfectly, every single time, which by itself proves nothing, since pre-written cards could manage that much. The interesting thing is what happens at the in-between angles, where the two detectors are tilted by different amounts. There, the rate of agreement follows a smooth curve as you change the angle, and that curve is steeper than any pre-arranged set of instructions is allowed to produce. It is as if you questioned two strangers with a long series of slightly different questions, and found that their answers tracked each other more sensitively than any pair of memorized scripts ever could, no matter how cleverly the scripts had been written in advance. The particles respond to the exact angle chosen at each station angles that need not even have been decided when the particles left their shared source, as though each particle somehow takes into account the setting of a faraway detector it has no way of knowing about. That is the impossibility Bell turned into plain arithmetic. Not that the particles agree, but that they agree too well, and too flexibly, across the whole range of possible questions, in a way no list of local, pre-written answers can match. A few years after Bell's paper, in 1969, 4 physicists, Clauser, Horn, Shimony, and Holt, reworked his result into a form that real, imperfect laboratory equipment could actually test, a version now known by their initials. It put hard numbers on the contest. In any local, definite world, a particular measured quantity must stay at or below 2. Quantum mechanics predicts that same quantity can rise as high as 2 times the square root of 2, roughly 2.8. The gap between 2 and 2.8 is the gap between Einstein's universe and Bohr's. It is not a difference of philosophy. It is a difference of almost a full point on a dial, waiting to be read. There is something quietly heroic and a little sad about Bell's position in all this. He had hoped the experiments would vindicate Einstein. He had built the sharpest possible tool for testing the dream of a definite, local reality, partly because he found that dream so much more reasonable than the alternative. And his own theorem was already warning him which way the answer would likely go, because the quantum predictions had been confirmed in countless other contexts and showed no sign of being wrong here. Bell had handed physics the means to settle its oldest argument, and he must have suspected that the verdict would go against the very intuition that had drawn him to the problem. He had made the unanswerable answerable. Now, someone had to build the apparatus, generate the entangled particles, set the dials, and actually ask the universe the question that Einstein and Bohr had argued about across 3 decades and never resolved. The answer would come, slowly, over the next 50 years, from a series of ever more careful experiments, and every single one of them would say the same thing. Part 11. The Verdict. The first serious answer came in 1972, from a laboratory in Berkeley, California, where 2 physicists named John Clauser and Stuart Friedman built a machine to do what Bell had only imagined. They produced pairs of entangled photons, sent them to detectors set at carefully chosen angles, and counted, over thousands upon thousands of pairs, how often the distant results agreed. Then they compared the tally against Bell's limit. The photons violated the inequality. They agreed more tightly than any local, definite world could allow, and their behavior matched the quantum prediction. It was the first direct experimental sign that Einstein's hidden, definite reality does not exist. The result was real, but it was not yet airtight. The equipment of the time left gaps a determined skeptic could still point to ways the universe might, just possibly, have produced the result by some loophole, while still being secretly local and definite underneath. The decisive step came about a decade later, in the early 1980s, from a young French physicist named Alain Aspect, working outside Paris. Aspect saw the most worrying loophole clearly. In the earlier experiments, the angles of the two distant detectors were fixed in advance, which left open a faint possibility. Perhaps the particles, or the detectors, were somehow influencing each other through some ordinary slow signal, conspiring to fake the quantum result. So Aspect built an experiment that slammed that door. In his landmark version, the setting of each detector was switched extremely rapidly, while the photons were already in flight, after they had left their common source. The two detector settings were changed so fast, and the stations placed far enough apart, that no signal travelling at the speed of light could possibly have carried news of one detector's setting to the other in time to affect the result. Each measurement was made before any word of the distant choice could arrive, and still the inequality was violated. Still, the photons agreed too well. With the possibility of any slow, sneaky communication ruled out, the quantum prediction held. Picture yourself standing inside an experiment like that, because this is the moment the whole story has been moving toward, and it deserves to be felt rather than merely understood. You are at one of two detector stations, far apart, in a quiet laboratory at night. At a source midway between the stations, a single event creates two entangled photons in the same instant, and they fly off in opposite directions, one toward you, one toward the distant station you cannot see. Neither photon carries any definite answer yet. The property you are about to measure does not exist in either of them. As your photon races toward you, a fast switch chooses, at the last possible fraction of a second, which question your detector will ask of it. Too late, far too late, for any signal to cross the gap to the other station. Your detector clicks. A result is recorded, a single definite outcome born in the act of measuring. And in that same heartbeat, kilometers away, the other photon gives its partner station an answer that is locked to yours, more tightly than any prearranged agreement could ever manage, as though the two photons settled the matter together in the instant of measurement, with no time and no way to confer. You did not find a hidden value that was already there. You and the distant station, between you, called a fact into being, and the universe coordinated it across a distance it had no local way to bridge. Run it again 10,000 times, and the pattern holds, sitting impossibly above the limit Einstein's world could never exceed. What the experiments killed was a specific, cherished idea, that the world is made of things with definite properties, sitting in definite places, influencing only their immediate neighbours. That picture, local realism, in the language of physics, is simply not how the universe works. At least one of its two assumptions must be false. Either properties are not definite until measured, or distant things are not truly independent, or, most likely, both. The comfortable world Einstein fought for, the world of solid facts, quietly existing whether or not anyone looks, is not a description of reality. The uncertainty we have been tracing all night is not a gap in our knowledge that a cleverer theory will someday close. It is built into the world. The blur is real, and after Bell and Aspect, there is no honest way to wish it away. Let us be careful and exact about one thing, in the channel's spirit of saying only what the data supports. This non-local coordination cannot be used to send a message. Because the result at each detector is individually random, neither station can control its own outcome, and so neither can transmit information to the other faster than light. If you only ever see your own side, you see noise. The impossible coordination shows up only later, when the two distant records are brought together and compared. This is why entanglement does not break Einstein's other great theory, relativity, and why no one can use it to build a faster-than-light telephone. The universe permits this connection to exist, but forbids you from ever using it to signal. It is non-local in what it correlates, and stubbornly local in what it will let you do a tension nobody fully understands, and one of the strangest truces in all of physics. It is worth saying plainly what was and was not overthrown, because the popular versions usually get this backward. Relativity was not broken. You still cannot send a message, an object, or any usable influence faster than light, and entanglement gives you no way around that limit. What was broken is something subtler and, in its way, more profound, the assumption that the world is made of separate parts, each carrying its own private store of definite properties, touching one another only through signals that crawl from place to place. That picture, called local realism, is the one the experiments ruled out. Reality permits correlations between distant events that no local, definite story can account for, while still forbidding those correlations from ever being used to communicate. The universe is stitched together more intimately than Einstein could accept, and yet it guards that connection so carefully that you can never exploit it. Think of it this way. Two entangled particles are not quite two separate things, trading secret messages across the gap between them. They are, in a sense, the mathematics makes exact, a single thing that distance has failed to fully divide. The space between them, which feels so absolute to us, turns out not to be the clean separator it appears to be. And if that holds for two photons in a laboratory, it holds, in principle, for any particles that have ever interacted and gone their separate ways, which is to say, for a great deal of the universe, quietly, all the time. The story has a final, human chapter, and it lands with real weight. The experiments grew steadily more rigorous, closing loophole after loophole, until in 2015, several teams in the Netherlands, and independently in the United States and Austria, performed loophole-free tests that sealed every remaining gap at once. The verdict was no longer in any serious doubt. And in 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for the experiments with entangled photons that established the violation of Bell's inequalities and opened the new science of quantum information. The argument that began at a breakfast table in Brussels had been settled in the laboratory, and the prize was given for proving the answer. But the man whose intuition was on trial was not there to hear it. Albert Einstein had died in 1955, still convinced to the end that quantum mechanics was incomplete, still certain that a definite, local reality lay hidden beneath the dice. The Nobel for the experiments that proved him wrong was awarded 67 years after his death. Being the greatest physicist of his age, and being completely honest about his doubts, did not protect him. The universe itself was asked, and it overruled him. And so we can return to that sentence, the one I asked you to keep. God does not play dice. Einstein meant it as an article of faith, a conviction that the randomness was a temporary mask over an orderly, definite world. After Bell, after Aspect, after 2022, the sentence reads as something else entirely. It reads as a beautiful hope that turned out to be wrong. The dice are real. They are not a sign of our ignorance, not a placeholder for some deeper certainty we have yet to find. They are woven into the foundation of the world, and the man who refused to believe it spent 30 years searching for a flaw beneath them that the universe, we now know, never built. The line he meant as a defense of reason has become, instead, the most famous wrong guess in the history of science, and a quiet reminder that the universe is under no obligation to be the way even our greatest minds need it to be. Sit for a moment with what this means for you, not for photons in a distant lab, but for you, here, tonight. The chair beneath you, the floor under that, your own hands resting wherever they rest, all of it is built from particles that, at the smallest scale, hold no single definite state of their own. The steadiness you have trusted your entire life, the plain solidity of the world, is not the bedrock you took it for. It is something the universe assembles on demand, moment to moment, as countless particles interact and force one another to take definite values, only to soften back into possibility the instant they are left alone. The definite world is not the rule lying underneath. It is the exception, stitched together continuously out of a deeper fabric of maybes. You are not made of solid things. You are made of a haze that becomes solid where it is touched. And remarkably, you can rest inside that fact tonight as easily as you rested in the old certainty, because the haze has been holding you up your whole life, whether or not anyone was looking. Part 12. What we know and what we don't. After a century of argument, after the experiments came in and the prizes were awarded, you might expect the story to end with understanding. It does not. It ends with one of the most honest and unsettling admissions in all of science. We know, with astonishing precision, exactly how the quantum world behaves. We do not know what it is. The mathematics is settled beyond doubt. The predictions are the most accurate humanity has ever made, and after all that, no one can agree on what the theory is actually telling us about reality. At the center of the confusion sits the question Schrödinger's cat was built to expose, the measurement problem, still unsolved after 90 years. The trouble is that quantum mechanics seems to contain two completely different rules. When no one is measuring, a system evolves smoothly and predictably, every possibility flowing along together according to Schrödinger's equation, the blur spreading and reshaping in a perfectly lawful way. But the moment a measurement happens, all those possibilities abruptly vanish, except one, which becomes the single definite result, chosen as if by the roll of the dice. Two rules, then. A smooth one for when the world is unwatched, and a sudden, random one for the instant it is measured. And the theory never says what a measurement actually is. It does not tell you what counts as an observer, how large or complex a system must be before the smooth rule gives way to the sudden one, or why definite outcomes appear at all. Everything strange we have met tonight, the blur, the uncertainty, the cat, the spooky correlations, flows from this single, unexplained seam in the theory, and physicists have been unable to close it. Modern physics has at least softened part of the mystery with an idea called decoherence. The insight is that no real object is ever truly isolated. Every particle is constantly being bumped by stray light, air molecules, heat, the surrounding world. And when a quantum system, in a blurred combination of states, interacts with its enormous, messy environment, the delicate overlap that makes interference possible leaks out into those surroundings almost instantly, far too fast and far too thoroughly to ever be gathered back. This is why you never see a cat, or a chair, or a person in an obvious smear of two states. The bigger the object, the more relentlessly the environment measures it, and the more impossibly quickly its blur is washed into the background. Decoherence explains beautifully why the large world looks so solid and definite, but it does not finish the job. It explains why we never see the in-between, yet it still does not explain why, out of all the possibilities, one particular outcome is the one that actually happens to you. The hardest part of the measurement problem survives. Because the mathematics cannot settle the meaning, physicists have proposed several different stories about what is really going on, and it is worth laying the main ones side by side, gently, the way you might consider several explanations for a dream. The oldest is the Copenhagen view, which says, in effect, do not ask the wave function is all there is. Properties become real upon measurement, and seeking a picture underneath is a mistake. The boldest is the many worlds idea, proposed by Hugh Everett in 1957, which takes the smooth rule at its word and throws out the sudden collapse entirely. On this view, nothing is ever truly random, and nothing is ever truly lost. Instead, every possible outcome really happens, each in its own branch of a constantly splitting reality, and the reason you see only one is that there are now many copies of you, each in a different branch, each convinced theirs is the only world. Then there is the pilot wave picture, the one descended from de Broglie and revived by David Bohm, in which particles always do have definite positions after all, guided by a real wave, a fully definite world, exactly the kind Einstein wanted, bought at the price of an explicit, built-in non-locality he would have hated. There are objective collapse theories, which propose that the sudden jump is a real physical process that happens on its own, more and more often the larger a system gets, so that cats really do collapse to a single state without anyone watching. And there are newer views, like the relational and information-based interpretations, which hold that the wave function was never a thing in the world at all, but a description of the relationship between an observer and a system, a catalogue of what can be known rather than what is. Here is the part that should keep you honest and a little humble. Every one of these wildly different stories, one world or countless branching ones, genuine randomness or hidden determinism, real collapse or no collapse at all, makes exactly the same experimental predictions. There is currently no measurement, none, that can tell them apart. So the answer to the largest possible question, the question of what kind of universe you actually live in, and whether your future is open or already fixed across uncountable branches, is at present a matter of taste. The smartest people alive cannot tell you which of these worlds is your home, and they are honest enough to admit it. There is something worth admiring in that admission, rather than something to resent. Science is often imagined as a steady march toward final answers, and in many areas it delivers exactly that. But here, at the very base of physical reality, the most successful theory ever devised hands us a flawless instruction manual with the last page torn out. It tells us perfectly what will happen. It will not tell us what is, and the people who understand it best do not paper over that gap with confident-sounding stories. They say, plainly, that they do not know, not because they are failing at their work, but because the honest edge of human knowledge runs right through the middle of this question. To sit with that is not a defeat. It is one of those rare moments when you can stand at the exact boundary of what our species has managed to figure out and feel, directly, how much wonder is still waiting on the far side of it. The uncertainty in the equations has a strange parallel in our own situation. The universe does not settle its smallest details in advance, and neither, it turns out, have we settled what those details mean. We are, in more than one sense, living inside an unfinished answer. This is also the place to gently set down a tempting misunderstanding, because the strangeness of all this has been borrowed for claims it does not support. You will sometimes hear that quantum physics proves the conscious mind creates reality, that because a measurement makes things definite, your awareness is what conjures the world into being, and that you can therefore think outcomes into existence. It is a seductive idea, and it is not what the physics says. The word observer is a historical accident of language. In quantum mechanics, a measurement is any irreversible interaction that records a difference, a photographic plate darkening, a detector clicking, a single air molecule colliding and carrying away the news. No mind is required, and no human awareness plays any special role. The radioactive atom in Schrödinger's box is measured by its own surroundings, long before any person lifts the lid. Reality does not wait for you to notice it, and it cannot be steered by wishing. The genuine discovery is stranger than the mysticism built on top of it. The world stays undecided not because it is waiting for a conscious mind, but because that is simply what it is, all on its own, in the dark, whether or not anyone is ever there to look. So where does this leave us, after the long walk from a glowing object in 1890-something to a Nobel Prize in our own decade? It leaves us with a universe that is provably, permanently uncertain at its base, and a theory that describes that uncertainty perfectly while refusing to explain it. Think back to where we began to Max Planck at his desk in Berlin, calling his own discovery an act of desperation, a reckless assumption he was sure he would someday explain away. He never did explain it away, and now we know why. The desperate fix was not a temporary scaffolding to be removed. It was the literal architecture of reality. The grainy, lumpy, undecided world that Planck could not bring himself to believe in turned out to be the world we actually live in, and his moment of desperation was, without his knowing it, the universe quietly confessing what it is made of. And think back to the blur, the image I asked you to carry from the very first minute's reality as something soft and undecided that sharpens into a single fact only when it is looked at. At the start, it was just a metaphor, a way to hold an idea we had not yet earned. Now you know it was not a metaphor at all. The blur is not in your eyes or your instruments. It is in the world. The sharpness you call reality is the thin, flickering surface the universe presents wherever its pieces happen to be touching, and beneath that surface, everywhere, always, lies the genuine haze of the possible. You have spent your whole life standing on that haze, and it has held you perfectly well. Nothing about tonight changes the floor beneath your feet or the breath in your chest. It only changes what you understand them to be, not solid certainties, but a steady, patient miracle of possibility, resolving itself into a world, again and again, quietly, without ever needing your permission. The universe does not have all its answers ready in advance. It decides as it goes. And somehow, out of all that undecided softness, here you are, a part of the haze that has become definite enough, for a little while, to wonder about itself. You can let that be the last thought as you drift off, not a fear, but a strange and gentle astonishment that anything is here to be uncertain at all.